today we want to talk about aligned sidewalls in project, end-wall to end-wall projects, aligned sidewalls. But before I get into that one, I would actually like to take a few, probably half the session, to go over wind edge zones, corner zone modifications for projects. And then after that, get into the aligned sidewall, what we've done for projects specifically, and follow that up with the bracketed support being now able to be on end walls with bypass skirts, and then anything up and coming after that. So starting out, I would like to just kind of discuss the edge zones and what that is. It's an area at the edge of the wall or roof, or it can be roof corner zones, and those areas are designed with extra increased pressure and suction on the components and cladding. Also, the edge zone area in this picture at the lower right here is area 5. It's called out on a few other diagrams. It's the same consistent thing throughout, but here it's showing you the corner zone, how they are. Those are the areas that do have the increased pressure and suction. I did have to go through quite a few building codes to try to figure out how to handle combined buildings and edge zones and corner zones and whatnot. And I did have to confer with a few people from MBMA. Dustin Cole was one of them, and then in-house people here. Came to the conclusion that for the code, I could come up with ways to modify wall edge zones for the ASCE 7-16. And that would be the IBC 18 has adopted that code. And so wall edge zone modifications are only applicable to IBC 18 at this time. Roof edge and corner zone modifications I found in both codes, ASCE 710 and 716, which includes the building codes IBC 12 and 15 and 18, and also the NBC, the Canadian codes 10 and 15. So there's a few things that will influence the corner zones at a building and due to the adjacent building. One of the things is how far the offset of the two buildings are, shown as X here. When it's a certain amount, the corner zone can not be applied. Again, this is for IBC 18, ASCE 7-16. An additional thing that influences this is the Y value, the differences in roof heights. Then I will also address the inside corner condition and when that applies or doesn't apply. And then the fourth thing that I've done with this is openings that are near the end wall or end bay have an influence on when corner zones apply and do not apply. My search of the code gave this figure as one of the big references. This is in the commentary of the ASCE 716. I do include the commentary to be part of the code. And so with this, I accepted this as how I were going to control when they do apply and when they don't apply. In this picture, you'll see that there's a corner zone 5, again, the same zone 5 for the wall. And then you'll see on the roof plan, there's a corner zone 3. I'm kind of zooming, I got my cursor around an outside corner. Both walls are 5 and the roof is 3. Zones 3 and zones 5 are applied together. I'll try to make that clearer as I get to that point. But for now, I'm going to really focus on wall edge zones at this point. But I just want you to be aware that wall edge zones do affect when roof corner zones apply. Inside corners, in the commentary, there is no edge zones required for inside corners. So that's shown in tan here. Neither wall gets added pressure or suction due to it being an inside corner. That's not something that applies with IBC 18. However, older codes are going to have those edge zones because I did not find anywhere in the older codes where the wall zones could be removed. So calculating A is what is considered the wall edge zone. It is calculated based on a few things. It's the smaller of, and everybody's probably familiar with these, 10% smaller of 10% of the least horizontal dimension, or 40% of the height, whichever value gives to the smaller, that's the one you're supposed to use. But as a minimum, it's not less than 4% of the least horizontal dimension, or 3 feet. The area L in this picture, can I remove that edge zone or not at the outside corner? Now, I'm not talking about the inside corner now, but I'm going to the outside corner. Can the L area have its edge zone area removed? The answer is dependent on how far the two walls offset each other. So when you calculate that A, as we previously showed, and then you compare that to the jog in the two building lines, and then that will tell you whether the lower wall area L, can be removed or not. And you just get interior zone loading then. To allow that to happen, we did have to make some modifications in the input files. So both in-wall design input and sidewall design input have added base values to the widths that we had for the left zone and the right zone. We added a base value. And so now in this picture, let's say that lower roof is at a 20-foot eave height. You can now raise that base up to 20 feet. Above that is where the edge zone applies, and it has a width of 12 in this example. So 20 feet to the bottom, 12 feet wide, goes up to the roof line, and now we can remove that edge zone with this new added base value. Here's showing you an aligned sidewall case. Of course, with an aligned sidewall, the building jogs are 0. They don't jog. And so in that case, of course, 0 is less than some calculated value of A. So in that case, you can remove those. And the tall building is shown here with its input file modified, the sidewall design input file modified. And it's showing that 8 and 20 like I had shown on the previous screen. And then in the short building, to remove the edge zone at that left corner, we set the width to 0, and then that removes it from the short building. So that's the way the L works. So can I remove the upper area, U, edge zone areas? Well, again, that's dependent on the adjacent building, and it depends on what the step in the roof heights are. There is a magic breakoff point of 10 feet. And so when your difference in roof heights is 10 feet or more, then you can't remove that. And so in that case, this upper roof is its own roof, and this lower roof is its own roof. They're separate roofs. In the other case, and in the case when the height is more than or equal to 10 feet, the corner zone and the edge zones both stay. Again, this is IBC 18 only, ASCE 7-16. So when you are less than the 10 feet height, then these are treated as a roof continuation. And what I did was I added this jog back in the building just to kind of let you see exactly what's going on here. So with a roof continuation, you have to have a little bit more going up to hit where this lower building's edge width comes up vertically up there, and then that has to, extend into that other building up to that inner point of that edge zone. When the area U is removed, then the roof edge and corner zone are also removed. The corner zone is removed. The edge zone is removed in the gable area above that inner point, but the corner zone is totally gone. So you don't have the additional zone at the corner in the case when the wall is removed. One of the issues with this deal is that we have to extend this up to the peak because we've broken these zones up where we're locked into kind of where we're at. And so we have to have this zone extend up to the peak. There's really no way to break that and not have it above there. And so we do extend that darker gray area up to the peak. And then on the lower building, since this has to jog up to where this higher building's inside edge is, that one also has to extend to the peak. So even though this is a roof continuation, these gable edge zones have to go to the peak just because of the way the input files are currently set up. The next thing I tried to address was openings in the end bay. These can form an outside corner. So there are a few of these cases that I've tried to address. And so I'm just trying to be conscious of this. I'm trying to make this automated for everybody. Everybody probably assumes that this should happen this way. I would have an outside corner in this case. So some of the things I'm looking for are opening in the short building, partial wall height, extending to the outside corner. So the in bay opening being the open type 4, if I have an open bay in the last bay or the start bay of the short building up against the adjacent building, then I'm forming an outside corner here, and I want to address that. I don't want the edge zone removed due to them being aligned. Same with the partial wall height. I've got an outside corner that forms here when I have a partial wall height, and I don't want those edge zones removed. I can also have a completely open wall, so I'm checking for that. So if you have your design detail wall set to no, where your sheets are removed, it's open, there's no girts, no anything like that, then you have an outside corner again, and I would not want the edge zone removed. Similarly, when the intersections in this short building and I got openings in the tall building, whether it be the open bay or the partial wall to corner or the outside corner with the design detail wall set to no, in all of these cases, I need to have that edge zone remain. And again, here with the input files, the way we changed these, the base is the only value that we have with these edge zones. And so because of the input file and because there's an opening at the end bay of one of the buildings and there's an outside corner formed there and I don't want the edge zones removed, I now have to keep these all the way to the base up to the floor. So in these cases where there's an opening and you're in IBC 18, which is the only one that gets modified, you may have these extending up and they may remain the full height. Roof edge zones. Okay, the roof edge zones have an extra code that allowed me ASC 716 or 710 and 716. I don't know which way that one went. 710 and 716 both had this stepped roof graphic. And so building codes that have adopted ASCE 7-10 are the IBC 12 and 15 and the IBC 10 and 15. And of course the IBC 18 is included with this, but roof edge zone modifications include these 5 codes, building codes. So this figure, if you want to know the exact reference, it's figure 30.3-3 in the ASC 7-16. And of course, there is a similar figure in 7-10. It may not be the same figure number, but it's very similar, same notes. In the figure, it is noted that this applies to flat stepped roofs. And so in the sketch, they do look like they're flat. And so I did try to find out what that meant. And so I was trying to determine at what pitch is a flat roof. And so I searched the code and I found that with snow, it calls for a flat roof, and it designates that pitch to be less than or equal to 7 degrees. And so I added that stipulation to this, where it is based on the less than or equal to 7 degrees. As we had seen before, there is a break off of elevation of 10 feet. That's the break off point. Less than 10 feet, it's a roof continuation. We kind of described that with the wall edge zone stuff. But here, this also applies here. The roof corner zone, when it's a roof continuation, the roof corner zone is not, that higher intensity uplift does not apply when it's a roof continuation. To confirm and cross-reference other manuals and whatnot, I did go to the Factory Mutual. I don't remember which year code it was, but I think it was the most recent one. But it had a data sheet of 1-28, and it kind of agreed with that 10-foot mark. And it said when you're above or equal to 10 feet, then they are separate roofs. It did show a corner zone on this upper roof in the tan, you can barely see it, tan hatched area. And then the edge zone along that gable, shown in a very light pink color, also remains. And when it was less than 10 feet, that data sheet showed that there are roof continuation, that corner zone removes, and then that gable edge zone in that upper roof is removed. And so just to cross-reference codes, I kind of came to the conclusion that they agreed with each other. So this was the verbiage from Factory Mutual, and it does talk about that roof continuation. This is just its verbiage. I threw this up here just so that you could see that it's documented in there. Roof edge and corner zones are removed when the upper edge zones are removed. So in that original C30.3-2, where it had an odd-shaped building, and I said that areas 3 and 5 kind of work together, roof corner zone was 3, and wall edge zones were 5. And so when wall 5 edge zones get removed, then that roof corner zone 3 gets removed. So this confirms what I said previously as an illustration. Okay, so this is the X less than A thing. This is showing you the corner zone is removed in those cases, just kind of confirming. So roof edge zone modifications, when the roof elevations are equal to or more than 10 feet, then we, in that case, have 2 separate roofs. And in both cases, that wall edge zone 5 remains and that roof corner zone 3 remains. And the gable zones are applicable on the upper roof. This confirmed with Factory Mutual and the code that we all go by, ASE 7-10 and 6. In this case, actually applied roof edge zone loading extends to the peak on one side, even though the roof zones aren't necessary. This hatched area, there's a note in this figure that talks about this hatched area in here and this lower roof. And it doesn't, what happens, well, the distance for this B is in a footnote, and B is equal to 1.5 times H1, and it can't be more than 100 feet. I didn't write that in there, but 100 feet is the maximum for that hatched area to extend. And what that hatched area does is the lower roof suction values, you can't really see it that well, but let's say this is a 1 and then this is a 1 prime. the one prime values become the same as the interior. In other words, there's no extra suction. They become the interior coefficient value. So the hatched area for suction becomes the interior zone. So basically, it's no edge zones when it's up against another building for suction. When it comes to pressure, there's a note in there that the pressure values become the same as the wall zone pressures from figure 30.3-1, and that is applied to that lower roof cross-hatched area, and so we've done that. Next topic, align sidewalls. So the conditions for align sidewalls currently are same building width, roof surfaces are going to be at different heights. The roofs can't really cross each other. You can't have a foot difference, one on a 1 to 12 and one on a 12 to 12, and they cross. You can't really do that. We don't accept that one. And then both sidewalls would align after you move them around and put them where they need to be and rotate them. So this is the conditions to run an aligned sidewall. The documentation for each of these is just about ready to go. I'm changing, I think 918.2 now, and I got one more to go through. So these will be out probably within a week. 2 of them are already there, but it doesn't do any good to have 2 out of 4. So if you wait a week, these will probably be there for you. The reference drawings mentioned in the enhancements are all kind of the same. I'm not going to go over all of the DT build values and DT methods. If you open each of these drawings, and again, they're in the enhancements, you can link from there, the enhancement. They would cover all of the DT builds and methods. So if you open each of these, you go through what you need to set. There are just a handful of markers from the marker files. I don't have them here, but they're in the detailing enhancement, which was the third one, 918.3. So just to make sure everybody's familiar with projects, I'm assuming that you are, but this is quick in case anybody is not that familiar with them, this is quick to get through them. You know, you'll click on your project icon, you'll see your buildings and whatnot. To go to the input, you do click on the building input button, which I have circled here. That will take you to the PDesEd screen, which has a way of entering in common data, which goes to each building, and you can skip that if you want, and you can go directly to the DesEd and do each building. And then the third step in the process is the build locator button down here at the bottom. And that takes you to this layout screen, the build loc. It'll jump you to the layout tab of that build loc. You'll have your buildings and you'll move them around. When you hover over a corner or over an intersection of a column and a wall, then you'll get this red anchor point that you can click and hold down, and it allows you to move. Once you move it, you can rotate it. They'll sync up and whatever. There are 3 tabs here, layout, intersection, and grid lines. You want to do each one. The intersection tab with the end wall to end wall has the larger rectangle, which you use to define which building includes the support and what the support type is. Then you also have this smaller rectangle within there, and it'll jump to the building that it contains the intersection. So I can see already that building 2 actually has this intersection of these 2 buildings. So when the first big rectangle is your building support type. Currently you have available independent, which 2 separate framings, 2 separate end walls, 1 in each building. Projected, you'll get some support from one of the 2 buildings to support the other one. The bracketed case, one of the columns becomes a bracket for the rafter. The projected intersection can have 4 different framing scenarios. You can have a rigid frame in one of the 2 end walls, and then post and beam in the other, or they can both be post and beam. In the picture here, you'll see that some of these columns can extend down to the floor in the top two views. In this bottom one, they don't extend down to the floor, they break. The reason is they don't align. So if you want the columns to extend to the floor, both buildings have to have the same end wall base spacing, only mirror of each other, so that they can pick that choice. This is the bracketed case. This is where the one building column becomes a bracket for the end wall rafter of the other one. At the time we released this, flush girts was the only thing available with this. There's a lot of interference between girt and purlin, and etc., clashing. So one of the choices was the bracketed choice. This is what a display of what you would get. The small rectangle, you have to pick your panels, whether it's open, and if you do have panels, then you have to pick the panel, the color, and then pick all the screws and styles and colors of trim. The third tab is, we went over the layout and intersection. The third tab is the grid line tab. Here you're going to want to preset your values for the starting corner, and whether you accept use the HI and O, and whether you want rigid frame interior columns to have grid lines. Click calculate, and then it'll do something, and then it'll populate these with numbers, and you can adjust those as you need, and you can pick between which axis you have. When you're done changing all this stuff, be sure you save. And then once you exit out of there, it takes you back to the build loc. And again, be sure you save when you get out of here, because that'll do a few things behind the scenes that need done. The new design considerations with the aligned sidewall. I've gone over the top two. The top two were the wall roof edge zone modifications, and then the wall edge zone modifications due for the openings at the end. Some other remaining ones that we'll just describe here are corner column. For the bracketed case, having a corner column remain in some instances. When there's a peak column and a rafter in the lower building supports the peak column, what we do there. The sidewall girts not being lapped, I'll go over that one, and then load transfer between buildings is a little bit of a subject that you need time for too. Recap of the wall edge zones being removed. Again, it was IBC 18 only. You have to have an X less than or equal to A, and you have to have Y less than 10. In that case, wall edge zones can be removed. Recap of removing the roof edge zones. Again, it's for 5 of the codes. X less than or equal to A and Y less than 10. Corner column remaining. So we don't really like, or haven't done yet, weak axis on columns. And so when you have a rigid frame at the end wall and you do a bracketed case, of course the intersection has to be in the taller one in order to bracket off of the taller column. The rigid frame at end wall case, when you get to the sidewall, of course the center of the rigid frame is in at least half the flange width, so you're not at the steel line, and the bracket that's part of that's the stub column of the short building, bolts at its outside face is at the steel line, and so you would need to extend something out and attach it for that bracket. We don't do that. So in order to not have weak axis bending, the only thing we're going to do is have the corner column remain, don't remove it. That prevents weak axis bending. So that's our solution for now. The next subject was a peak column. You can have a peak column in the tall building with the intersection in the short. For those cases, we do kind of expect an S3 splice. It can be an F splice. We would do the same thing, but we just don't want the S splice with the loose plates on it, or any of these weird non-S3 splices. We want just the welded plate where they kind of stop and start, and then we can add in a clip or extend one plate or do one of our normal things that we do when there's a column below. And so to make that happen, when you pick a shear splice that's not an S3 for your peak splice, we automatically switch it to an S3. You don't really see it, it happens. It's behind the scenes. We need it to be an S3 in order for the detailing to work, and so we automatically switch it on you, assuming that you didn't realize. Sidewall girts are not lapped between buildings. We kind of feel like that's going to be the easiest way to do these, to erect them and whatever. You ship one building, you ship the next building, it goes up. You have to have one building up before the other one goes up. If you lap girts, you'd have to ship the sidewall girts from both buildings. Be sure they're both on the site. For us, it was easier to do them separately. I mean, there's a few reasons, but anyways, with the intersection in the, so there's a few reasons why we didn't. You can have, there's so many variables. So flush or bypass in-wall girts, flush or bypass sidewall girts. The corner column can be rotated, rigid frame, or it can be non-rotated, and the intersection can be in either one. With all of these different factors, we thought it was easier if we just break them apart and have them in their own individual buildings. So the sidewall girt that's so one of the buildings has the intersection, the other sidewall girt's coming in, and what is it attached to at the corner? Well, it attaches to whatever's at the corner. So if in this first case, upper left, you see that there's a flush corner, then the column is at the corner, and the only thing that the adjacent girt can attach to is that column. So we'll attach to that. If that column is moved in, like in the next two down from there, then we attach it directly to the sidewall girt. If that sidewall girt isn't there, or at a different height or whatever, and we don't have any way to do it, then we'll again attach it to the column. If the in-wall girt goes to the corner, then that's what's there, and if they're at the same height, we attach to that. And in most of these cases, we're using an R clip. So we basically attach to what's there, whatever extends to the corner and is at the proper height, we'll attach to that. As a last result, we attach to the corner column. Load transfer between buildings. Again, the blue is going to be the loading, and the red will be the reactions applied to the adjacent building. So with vertical loading, all shown in blue, the reactions from the columns will go directly down to the rafters below. With the intersection in the short, again, the horizontal loading, half goes to the top and half goes to the bottom, kind of typically what we do. The green going up goes into the bracing system. The yellow goes directly down to the supporting member below. So there's a couple choices for bracing systems for an end wall. One of them was the X bracing, and one of them is panel shear. So we special treated panel shear to be based on what the column's linear distance along the base is. So if let's for example say I had 20-foot base here, and the first column would get a 10-foot portion, the second one would get a 20-foot portion, the next one a 20-foot portion, the next one a 20-foot portion, and the last one would get, again, the 10-foot portion. So whether it's a rigid frame or an end wall, we will be putting these point loads in for panel shear in this manner, because that's the best way we can model it. If you had X bracing as your bracing system, then these green arrows would transpose into these red arrows as reactions. Again, this is just the top portion of the horizontal load in the top building. So you get an uplift with this cable pulling over that way, and you get a downward load on this one. And the three arrows that you see here are what you would get as imposed loadings on the lower framing. Of course, left and right direction, these would reverse and go to the opposite column for the horizontal portion. If the intersection is in the tall building, then again, the blue is the loading on the lower building. The reactions are shown in red again, and they would be point loads on the inside flange of that rigid frame column and those interior columns, or point loads vertically on the end wall columns. The wind load, I just did a big arrow, it's all normal to the surface or whatever. The wind load, which way did that go? Applies horizontal reactions to the columns, but we can't handle them in this, putting them where they are shown here. And we have to transfer them up to these red locations, and that's the best we could do at this time to get this model to be as close as possible and account for the loads that are actually there. So the blue are the reactions from the plane being loaded, but the red is how they're applied to the adjacent frame. That was the wind load on the roof. This is the wind load on the walls. The wind load on the walls is similar, half to the base, half to the top. The ones that go to the top, again, are transposed up to the top to be surface loads. So in order for them to get into the bracing system and with the rigid frame is the frame itself. Bracing system with the X bracing would be down through here. So in order to get these loads into this upper bracing system, we move them upward into that upper rafter. Verification. So there are two tools to use to verify that these loads are applied as you expect them. I've done the calculations. I've seen the loads come out like I expect them. I checked them, and then they seemed right to me. So the action program would allow you to see end wall or rigid frame adjacent building loads being applied to the supporting frame. In this case here, this is a lower rigid frame or lower end wall having the intersection. This shows that the vertical loads are applied at each column. The red shows that there's a big horizontal load. It's the base reaction plus its portion of the horizontal load. The green is shown here because there are different uplift values. One was increased and one was decreased due to the pull with a cable, and then there's an additional horizontal load on one of the two columns, the one that was in tension. To verify that the edge zones are removed or not removed or whatever is going on, you should use the DesCalc graphic. In this case here, you'll see this wider edge zone. This is up against an existing building. You'll see that this doesn't have the wall corner zone. This one doesn't have any. The roof edge zone is that wider 1.5 times H1 value that was up against an existing building that was per that figure. Oh, okay, so yeah, so that's where we're at with those. Those were all the design considerations. I wanted to see if you guys had any feedback at this point. I see I'm on not very good here. Could the horizontal loads be considered to transfer axially through the lower rafters and be applied at the sidewall rigid frame columns rather than transfer up to the roof? I don't know the answer to that one. I'll have to get back with you on that one. I'll have to check with my programmer. I'm not sure what we can do. When it modeled correctly, it is the goal. So I do got to kind of keep my pace up. So next 15 minutes. Next aspect, I know. I don't think it's enough time. Next aspect is the detailing considerations for the aligned sidewall. We made some changes where now that those short rafters can attach to the rigid frame inside flange. That's new. The peak column above to the peak splice. Corner column above to the rigid frame. That was never available before. Corner column being pitched on the base is new. Moved some slots around for the short rafters. We made an east strut attachment when the intersection's in the tall building with the east strut attachment for the short. And then we've made full depth stiffeners when there's a column above and below at the same location. And I'll go over each of these with pictures here. The short rafter to rigid frame inside flange wasn't available before. This also prevented that short narrow case that we first did from allowing to be in the end bay. Now that restriction that we had before is gone because now we can attach to the inside flange. So the short narrow building can now go to the end bay. It wasn't that big of a concern, but that was what everybody was running the first time out the chute. So that is now available. The peak column splice, again, this wasn't there before. We do now attach to, based on this method, either the rigid frame peak splice or the end wall peak splice. You'll have to set a method for each of those. I think 125 is the one for the rigid frame. We did reuse 125, so whatever you do for the top, automatically you don't have to set that one, but the end wall one was new. I think it's 569. Method 569, you have to set that one. Corner column above the rigid frame, that wasn't available before. It is now working. The gap. Usually you'll have a sidewall, girt depth in here. It's usually the same above and below. So the outside of flange of the rigid frame is usually in line with this outside flange. The other thing is the column bases didn't used to be pitched. That used to not be available. We can now pitch them either direction. We can pitch them along the web, or we can pitch them across the flange, as you see on this left side, which we could do that before. We did alter the brace locations for the cables. When you have the short rafter coming into the columns that go to the floor, we now move those above and below the rafter locations by the ER value. That's a pretty old parameter. We're just using the gap that you set for something else. We're applying it here. We're assuming it's enough clearance for the other case, so it should be enough clearance for this one. With the E-strut, again, tall building contains the intersection, so you got things from the sidewall extending out from the short building, short building. Sidewall girts need support, and the E-struts need support. E-struts come through. There is a corner column there. It can be rotated, it can be standard, or it can be a rigid frame. In any of those cases, when the girt is bypassed, we will weld a ledge on there. So in this top view, standard column, not rotated, we will weld a ledge to the web. If you had the rotated corner column, we will weld the ledge to the flange. And if you had a rigid frame, we would weld the ledge to that outside flange too. If you had flush girts, we will do a loose bolted clip. We will pitch the holes in the clip so that the column has flat holes straight across. We figure that's the simplest connection. In two of those cases, you probably have to notch your clip in the field. We don't really notch the clip for this. Flange thickness or whatever. You'd have to probably field notch that for a rigid frame and rotated corner column. The other thing we did automatically for you is when those columns are at the same location, we did do a full depth stiffener and make it vertical. If your options are to have them perpendicular to the flange, we still make this case vertical for you. Another thing we're doing is we mix the two sidewalls together when it comes to detailing the panels. So if you had, let's say, 3 200-foot long sidewalls aligned all together, you would get 200 panels that are 3 feet wide, as opposed to 3 that cover 200 feet, which would be an extra 2 panels probably. Okay, any comments there? Always 1. Always one stiffener, not two. Is there an option for a bolted clip to E-strut off the flange instead of welded? Nope, not at this time. Can you control the location of the panel splice? I don't know that I understand that question.
We'll get more from Randy and continue on.
All right, next topic. So we did have a bracketed bracketed support available. It did have flush girts only on your end wall. So your end wall had to be flush girts in order for you to have this choice available. I'm the one controlling the choices, and so when you had bypass end wall girts, I didn't give you a choice to pick bypass girts. The reason is because when you have flush girts, everything is so smooth in here and you don't have any conflicts that it just didn't warrant to do bypass girts. We got some pushback from the international clients. They commonly do bypass end wall girts, and they just kind of wanted that to happen. And so we opened it up to do that. There is a few things needing to be noted here. What happens is you'll get this extra welded stub thing that's like an eve extension bracket kind of thing to come out and support that bracketed column. And so what we do is, this all along was pretty simple. We had one connection, and it was a shear connection between the two flanges of the two columns. Direct bolt, just call that a shear connection. So when they wanted the bypass end wall girt, we made this still be the same shear connection between the bracketed column and the end plate. We still designed this column and always have designed it for the eccentricity, so we're still doing that. And then the welds on this bracket are designed for the moment induced due to this little eccentricity here. So when it comes to the design of this, we are accounting for this eccentricity, applying that to this column when we do that. But this is still a shear connection out here. You will see that in the reports. It does appear in where it normally is the base plate. We report this shear design of this connection. Smaller calculation of A. It was pointed out by one of my people that gives me feedback that calculation of A may be in question. So going back to one of the original slides, the smaller of 10% of the least horizontal dimension, 40% of the height, but not less than these other couple things. So a note in this figure from ASC 7-16 was that this applies to buildings with non-rectangular plans. And there's a note that the least horizontal dimension is determined by a rectangle that encloses the plan view. So that's what you kind of have to go with. I'm not really trying to paraphrase this. You would want to go to the code and look for this verbiage yourself. But my question would be okay, this one still looks like a rectangular view. So rectangular plan view. Is this one rectangular plan view? I don't know. This one here. In each building directory, when we're doing these projects, we do slam in there a couple of files that have a bunch of information in them. And so each building directory has information about the other buildings, where they're located, what their sizes are, what their roof pitches are, etc. And so the edge zone can be calculated in a couple different ways. Each building does do its own calculation of A. Period. Already does that. So this is a poll question. What is the least horizontal dimension for calculating A? Would you assume it is the building dimension or the project dimension with a big rectangle around it?
Big rectangle around all the buildings.
Came out right around 47, 53. Amazing. So just to let you know, you can pick whichever one you want because I have a switch for each one. The default will be buildings. So
individual.
based on your building size, that's how it's going to use least horizontal dimension. You can put in this switch in here. Oops, can't click on that. Put the switch in here, which would say, these will be in the enhancement. They're not in there now. Wind edge, horizontal dimension equal project. So those will be available. They will affect the A calculation directly. Another thing to kind of question was what height would be used for calculating A. Part of A was 40% of the height. So is it building height? Or is it like the mean roof height? Oh, another thing with height is when you're calculating the basic wind pressure, you're calculating KE, you're going to look up table. Part of that is due to height. You'll have a different number. Of course, it allows interpolation on that graph. So it can be these choices here. I'm going to have another poll question. Of course, conservative would be the maximum building roof height of any building in the project. So let me launch this last one. Which height would you use when you're calculating both A and the KE value when it comes to the basic wind formula? Would you use the building height for each building? Would you use the project mean roof height, or would you use the maximum building roof height of all of them?
Then, wouldn't it be KZT rather than K sub E? K sub E is the elevation of the building above sea level.
Okay, it might be one of those other ones.
Or more simply, KH or KZ.
I thought it was KH, but then I switched them all to KE because I see E said elevation. I thought, oh, that must be it. 4% would use the building height. I don't know that that's a problem. Again, there's a few things that enter into the calculation of A, least horizontal dimension and height. One of them is going to control. These were, again, just curiosity questions for my own sake. I do have a switch for each of these, and if you're more than welcome to use it. Again, these will be in an enhancement at some point here soon. Wind edge zone can be mean roof height equals building, mean roof height equal project, or mean roof height equal building max. So I've got a couple switches already available for that. Okay, what's next? For me, I see aligned roofs in my future. Kind of started delving that direction. And so I was going to show you what is being proposed, and I can already hear the ahs, but roof surfaces designed independently, purlins not lapped. Those are the two things that are going to be awed.
So we did lots of fun with this. I mentioned in answering some of the questions about comparing the optimization of the roofs. And when you get two buildings that are of a particular length, or not short, shall we say, not a couple bay scenarios, in order to get the purlins to lap, you are forcing the optimization of one width building to be the same as the other, which is causing one building to be heavier than the other. And what you're comparing that against is a two-lapped or continuous condition for the end bays only of those two buildings. So if you had two very short buildings, i.e. one bay, where some of the purlins could lap, but the widths were different, it might make sense. But when you have scenarios like shown in the picture of any length of those buildings, you're actually adding a lot more weight to the structure by forcing the purlins to lap.
One other aspect of this is we are reducing the edge zones when possible. So even though they're not lapped, they may get down to the 16 gauge because there's not edge zone suction on them. So bonus. So anyways, here's a cross section of what we're attempting to do here. So we're going to have purlins in one building be their normal support by clip or direct bolt, whatever. To the end of that, and this is at the building line as this dash line, at the end of that, we're going to attach loose clip, bolt on a C or O or U or something web to that bracket, and then bolt bracket to that, and then bolt the purlin to that. So loose clips in a couple cases there on each side of that rafter. It's supported. This allows, you know, purlins in this building to be anywhere and purlins in this building to be anywhere. And so you can design them independently. They're located where they need to be based on the optimal location, and you get the least weight in each building. It should somewhat be the least weight overall. If you had an intersection panel here, we have another setting to gap that out some more to allow that rafter to not conflict with the high ribs of the panel and screw heads and whatever. After a lined roof, what's next? I still have the couple cases of the short narrow being on top. These are end wall to end wall cases. And then the one I'm dreading, and everybody probably more needs, is this staggered case. So those are the ones that are in my future. That's kind of the end of my webinar. Just wanted to see if anybody had more questions. Well, I'll give you guys a couple more minutes. I know I went past by a few minutes. If you wanted to shoot me any more questions, I'd be more than happy to answer them at this time.
Thanks.
Yep, thank you.